One other place we can apply L'Hopital's rule is to what we call indeterminate powers, limits that are in the format of 1 to the infinity, 0 to the 0, or infinity to the 0. Before we see an example of one of these indeterminate forms, we first need to establish something about limits. So let's say we have a limit. X approaches a of f of x is equal to the number L. One of the theorems we saw in chapter 2 is that if I take a continuous function and apply it to both sides, I can actually move it to the inside of the limit. What I want to do is imagine a particular continuous function. I want to take the natural log of both sides of this equation. So the natural log of the limit here is equal to the natural log of L. I've done the same thing to both sides. The continuous function theorem I'm talking about says I can rewrite this side as the limit as x approaches a of the natural log of f of x. Well, it turns out that that theorem works in both directions. It's an if and only if. So I was thinking about kind of deriving this, like this line implies this one and this line implies this one. But if I start here at the bottom, I could work my way back to the top. If I had this as a true statement, then this is a true statement as well. So I want to put us in a what if. What if, instead of calculating this first, instead of this being the thing I was given, I was actually given a statement that looks more like the one at the bottom. That I was able to evaluate the natural log of f of x to be the number, say, m. What then would I be able to say about the limit as x approaches a of f of x? All right, well, that's like starting down here and going backwards. That if this equaled the natural log of L, then that limit was L. Okay, well, this gives me a point of comparison to make. M is standing in place of what was the natural log of L. So I'm just calling this limit M, and it was the natural log of L. This limit's supposed to be L, so let's get L by itself. Well, L would be the base e raised to the m power. So L now is e to the m using the property of the natural log. So if I can calculate the limit of the natural log of f of x to be m, then the original limit would be e raised to the m power. This is how we'll approach these indeterminate powers. For example, one thing I should say. Here I have the limit as x approaches a. And that a could be a number, it could be any constant, it could be approaching from the right or left, and this statement would hold. A can also be infinity or minus infinity, and this statement would hold. Okay, now an example. The limit as x approaches infinity of 1 plus 1 over x raised to the x power. Now, this is a limit we've actually evaluated before. I won't remind you of what the answer was, but maybe pause the video and give yourself a chance to see if you can remember what our answer was. Okay, as x approaches infinity, the inside is going to 1 because this part's going to 0, and the top is infinity. So this is the indeterminate form, 1 to the infinity. I'm not going to answer this question yet. I'm going to ask myself a related limits question. I'm going to solve this problem. The limit as x approaches infinity of the natural log of 1 plus 1 over x all raised to the x power. Because again, if I can solve this question, then the answer to the original one is e raised to the limiting value I got. By introducing the natural log, I can rewrite that power out front. And now what I have is x goes to infinity. Well, x is becoming infinite. The natural log of 1 plus 1 over x, that part's going to 0. The natural log of 0 is 1. Excuse me, the natural log of 1 is 0. This is an infinity times 0, which I can then rewrite as the natural log of 1 plus 1 over x all over 1 over x. Because multiplying by x is the same thing as dividing by 1 over x, and now I have an infinity over infinity. what started off as a 1 to the infinity, we rewrote as a separate problem in the format infinity times 0, and now we've made that into an infinity over infinity, which I can apply L'Hopital's rule to. The limit as x approaches infinity of the natural log of 1 plus 1 over x, all over 1 over x. All right, L'Hopital's rule says I can take the derivative of the top, so that would be 1 over 1 plus 1 over x times the derivative of the inside, and that's minus 1 over x squared. And the derivative of the bottom is minus 1 over x squared. Those cancel. And in a very rare thing for me to do, I'm going to leave this as a compound fraction because it's easy to work with. The limit as x approaches infinity of 1 over x is 0, and I'm left with 1 over 1 is 1. So this limit, its answer is 1, which tells me that my original limit was e to the first. Hey, this is how we defined e much earlier in the course. All right, so there's an example of an indeterminate power.